So thank you very much, first of all, for the organizers for taking this opportunity in this situation. So that's not easy to organize and get all together, and for this interesting, in fact, workshop that we are having. So thank you for this. And then what I will present is some recent work related. So it's a long title, but I like to point out the key words, which is the oscillations. Okay, so dealing mechanical models that do reproduce the oscillatory behavior that we see, and there's a rheological model for the cells that can reproduce and based on delay. Okay, so that's also the key aspect. But I will take also the opportunity to present how the mechanical model we are using that is based on vertex models, okay, besides other continua that I will present. So this has been done in the last year, so with Peyman Mosafa, Malik Dawi, which are at UPC, one's postdoc, another is a PhD, and Pablo Vicente and Rob Tedley, who are postdocs that work at the lab at Yan Lan Mao lab at UCL in London, but who have been doing experimental work as well, where we don't do at UPC. So this, the manipulation is done in London for this work that I will present. So with that, let me motivate my talk with some oscillatory aspects. So the one on the left was some observations done by Jérôme Solon during the Drosophila door closure, who is in Spain. But so you look at the movies, fast motion, so it looked like a fluid, although there is no inertia. So this has been known that these massless oscillations, so there must be something else besides the viscoelastic behavior to reproduce that. So because in time they are first order differential equations, so we would not have oscillations unless we add something in the fluid. So what you see is during the closure of the Drosophila embryo, so cells and the fast motion, they oscillate as if you would see a fluid. So in a very synchronized manner, in fact, and a very sustained. And whether these oscillations trigger further morphological processes, so it's still an open question, but we are looking at that and trying to model these oscillations into the mechanical models that we have. So on the right, what you have is cell spreading, and these oscillations have been also being observed. So what you have is a chemograph on the right, where the vertical, you have the mean position of the cells. Okay, and what you have the colors is the velocity, and horizontally what you have is time. So for each time, you have that the velocity, in fact, travels with a certain speed that would be the slope of these traces that we see on the contour plot that we see on the right. So this has been done during cell spreading. There's these oscillations traveling, okay, which are of the order of minutes. I point out that on the left, this has been also put together with the myosin signaling, and in fact there is like a myosin signaling of order of 3-4 minutes together with these oscillations, with also a period of 3-4 minutes, and they're very well synchronized, but with a delay between them. Okay, and the models that we have been using is continuum models with finite elements that I will show some of them, but we were extending because what is happening at the cell-cell junction, it also matters. So it's by construction, it's a continuous system that we have. So in order to have the forces at the discontinuities, we resort to a vertex model that I will show with a 2D how we can introduce these oscillations. 2D and a half, which I told, which somebody said that is like a constrained 3D. I say 2D and a half because in fact it's constrained to be on a monolayer, so we don't have vertical dislocations. And then a fully 3D, that is something that we have been now developing recently in order to reproduce other systems, things that happen in 3D. So with this, let me also show another system where we have these oscillations. This is a wound healing, which was really well studied in 3D. And we also see this oscillatory behavior of the cells. The cell boundary here has been stained. What you have in the center is the wound helix, so it's wounded, and then it expands. There's a recall process, and then the closure due to a contractility. And you have other systems that expand, but this is cell proliferation. Okay, so it's which we don't include in the models, but we're interested in what's happening in the center. So on the right, you have the similar also process. Maybe the light can be maybe switch off on the front, because we'll be seeing that it's not fully flat as we see on the left, but in fact it's 3D because there's a myosin signaling here in the center, as we can see here. So it forms like a cone. So it's not like two fronts that close together, but in fact it's rather a closure that comes from the bottom to the top, forming a cone, because the myosin signaling is not completely flat at the wound edge. Okay, so that's also interesting features of why it closes in so robustly. And so it's a scarless during embryogenesis. You don't have a scar for the wound closure, but when adult tissues, you do have a scar. So there's the interest of looking why it closes so well here and not in the adult tissues. So this is one of the motivations, the wound healing, but still with the oscillatory manner. So that allows also cells to intercalate during the closure, and we will look at that. And the last phenomena, so this is again the Drosophila. Before was the Drosophila fly wing, and this is a Drosophila fly neural ventral cord, which is in red, cannot see due to the light maybe, but you have the epithelia which is surrounding the embryo. And this is the neural cord which the flies have on the, it's like our backbone, but they have on the ventral side, and it condenses. So there is a condensation process, and it condenses due to also the dragging due to a retraction from the back, okay, with other organs that are there. But this condensation seems to be pretty autonomous, but is also what we have observed is that where the people that have done the measures, that is a collaboration with people in Barcelona and in Singapore, so that it also oscillates, as you see on the left. So you have, which is the velocity that is going, what is the lines on the right is negative velocity, so going toward the anterior side, and the ones on the left is going towards the right. So there is a condensation process with a fixed point somewhere here in the middle where it condenses. So this is the lobes. So this neural condensation is in fact coupled with the formation of the brain, which for the fly is basically the optical lobes. And we're interested in why these oscillations are there, so there must be something trying to explain that. And we couple also with a finite element that you have on the right. So this is a projection of all the images, okay, that you have for this segmented structure that you have for the epithelium and the neural cord. So what we saw is that this segmented structure, what you have on the top is on the right is the finite element model where we map the velocities, and at the same time we solve the viscoelastic equations, linear viscoelasticity despite the deformations, but doing a sequential problems of viscoelasticity. And we see that the segmented structure is also preserved, but in a detached from the segmented structure that you have for the epithelium. Okay, so the two segmented structures, they don't go together, but they detach each other. So there is some friction interaction between the ventral cord and the surrounding, the environment that surrounds it, which is the part of the epithelium. So there's been some mechanical measurements in order to quantify the viscoelastic properties. And one of them is looking at the characteristic time, so how much viscosity versus elasticity you have along time progresses. So the stages during developmental process. So earlier it seems that viscosity is high, so viscosity is being reduced, or elasticity is being increased. So it's the ratio of the viscosity versus the elasticity. So the characteristic time of the system is being reduced. And at the same time, this has been measured of the rigidity. So in the earlier stages that you have in here, so it's also in agreement with this reduction of the characteristic time, is that the rigidity also increases. So either viscosity reduces or the rigidity also increases, producing a reduction of the characteristic time. There are other mutants which I won't talk though. This is done in the analysis, but I won't go into the effects on the mutants. Right. So this is with these basically two systems, this condensation process, and plus the wound healing that I will talk about in order to relate that to the oscillations that I mentioned. So with that, let me present the model, which is very, very simple. The idea is that, in agreement with what we see in the dorsal closure also, that there is oscillation and there's a delay between when the cells can feel and what they exert. So there's the stresses sigma are proportional to the elastic strains. So this is a 0D model, okay, a point model. So they're just proportional with this rigidity key, and we will have here with this rheological picture. But there is the change is that the rest length, which is the length at which there is no stress, this is capital L. So it changes in time, okay, in proportional manner to the elastic strains, which is the measure that we will have here, standard linear strains. But instead of the L0, what we have is a capital L, which is the rest length, okay, the length at which would be no stresses. So it's proportional to my L dot changes as far as epsilon E is equal to 0. Let's ignore this epsilon C, this contractility so far. So there will be no changes of rest length if I have no elastic strain in my system. Now, if we add the epsilon C, what we do is there is no changes in my rest length as far my elastic strain is equal to a given contractility that we have as a parameter. So this is the preferential contractile state that the tissue wants to be at. Okay, so when the two are equal, then the rest length doesn't change anymore. And this has been some experiments in UCL done by the lab of Björn Charratz, where in fact you can measure these contractile strains doing some compressive, so looking what would be this epsilon C, and it tends to be something like around 15%, okay, for some suspended tissues. Okay, so it's something measurable, and the rest length, in fact, is something, although this rheological model, when you insert and you look at the progression of stress relaxation or creep that you have, is similar to a Maxwell model, very similar. It works not with viscous or strain rates, but instead of rest length, which is something that is measurable. So that's why we prefer to work with that. And but it has very similar response to what you would have in a Maxwell model. Okay, and this gamma here, it's like remodeling rate, is how fast the rest length adapts to the difference between elastic and contractility strains. Okay, and has been used in embryological models in those references, for instance. Okay, so that's not that has been useful for some cases. So now, but if you include this model, of course, this is similar to a Maxwell model where you don't have oscillations. But what would do, how to reproduce oscillations? So what we introduce is a delay, okay, with the idea that we have in a dorsal closure that's saying what I adapt, my rest length does not adapt to my current elastic strain, but to what it felt some tau time before, some delay. Okay, we introduce this tau here, so similar expression as we had before, so the evolution of L, my rest length. So the time derivative is proportional to the difference on the length, but not to my current length, but to the length that was some tau time before. Okay, this is a delay differential equation, which have been well studied in mechanics, but not as much for biological systems, as far as I know. But they have a very well characterized response. What you have is a limit. A threshold for oscillatory behavior, okay, and a threshold for stability. So, and this is proportional to this gamma, to the product of gamma tau, so the remodeling rate and the tau. So if tau is too high or gamma is too high, then the system becomes unstable, as you would see here, okay, when you have my delay is higher than this limit that we have here, that is equal to pi over 2 gamma. Yes. Okay, so then the oscillations become more with a larger amplitude, so they're unstable. And whether in between, you still have oscillations, but they diminish, okay, and they dump out. And if you have some tau that is just below this oscillatory threshold, in fact, you don't have oscillations at all. Okay, how you get these bounds is by looking at the characteristic equation, which, okay, is related to Lambert function. but you can deduce these bounds in a fairly easy manner. Okay, but in a similar way that we would do for ordinary differential equations, but in factoristic equations, it's not a polynomial, has an exponential in it. But you can get these bounds. The problem is that we get the oscillations, but the oscillations either unstable or just diminish. And rheological systems do not behave like that. Okay, so we still have a problem to reproduce sustained oscillations here. So we added two ingredients. Okay, one is because of this, or the central neural core, we have the environment. So we add some friction with the environment, which will be this eta at the boundaries. Okay, we had in parallel also another spring, which is not fully necessary, in fact, in the model. Okay, we realize, but in order to, okay, we can set that to 0. But so my equilibrium equation is that all my stresses, elastic stresses, are equal to my friction forces with the environment. Okay, that would be the differential equation, together with the same delay differential equation that we had together. So everything in a compact manner can be written like that. Another delay differential equation, we have tau here. And again, we do have oscillatory behavior, and we can have also not analytical bounds, but some other phase diagrams. Okay, we have more parameters, so the phase diagrams are a little bit more complicated. I won't look at that. Everything was a little bit like expected. If gamma increases or tau increases, then becomes more unstable. Okay, that was somewhat expected. Okay, but what was more unexpected was this that we have here at the bottom left, where in fact we see that if my eta, so my friction that I have here in the vertical axis here at the top left, so this value, if it increases, it becomes more unstable. Okay, and not normally in mechanical systems. So in this system, we would expect that if my viscosity or my friction increases, should stabilize the system. Huh? Okay, so that's what we said, but it's not the case. And what we have in a dashed line in all the diagrams is this bound for the sufficient condition for having instability. Okay, we don't have an analytical bound as we had before, but looking at the characteristic equation of my previous DDE, we also have these bounds. So wherever this is about the limits, and we have stable behavior. So what we have that we are sure that we may be unstable beyond this limit here. So and this is the case because this corresponds to one of these curves here. No? For gamma equals 0, I don't know, you can be seen, and tau equals 6, which is the last one here. Okay, so at least we have stability below the right of this dashed line. And the same, so it reproduces this behavior that higher elasticity becomes higher friction, eta, we have more high instability. We can interpret that in the sense that when we have more friction, it's like introduce a delay of our response of the stresses. So it goes together with the same effect that an increase of delay we produce in the system. So that's our physical interpretation of why this higher friction stabilizes the system. Okay, and that going back to our system of the neural core, where we have a decrease of the characteristic time, which is that my viscosity decreases or the stiffness increases, in that diagram would be that we are going from some unstable behavior here in this area, top left, to more stable behavior somewhere here. Okay, so it's going diagonal towards from the stable region to the stable region. Okay, with the decrease of the characteristic time. So it agrees with the stabilization of the system during this condensation process due to the viscoelastic properties that we have. Okay, so still in that system we have the oscillations, but it depends on the parameters, but they are not sustained. So either it's unstable or either is unstable. So what we further introduce is saying, okay, my strain measures, okay, are not the same that we had, but we include not the displacement-based stresses that we had later, but the strain-based, denoting in this branch, this K2 corresponds to in fact, to that branch. Sorry, because K1 and K2 they are swapped here, because this K2 is proportional to my rest length, that is the top branch that we have. So this K1 and K2 that we have here. So this is a nonlinear strain measure because capital L depends on time. Okay? And so the same equation that we have, the equilibrium on the top and the evolution law for capital L for my rest length on the bottom. So this can be interpreted, in fact, as a very similar to what we have, if you linearize, as having a nonlinear K1 and K2. Okay, where K1 and K2 are given by these expressions here, which are got. So similar as before, but when you linearize around a given L star and capital L star here, so it's like going across the stable and unstable region with changing rigidities K1 and K2. So you attain this limit cycle. Okay, now the oscillations are sustained in time, and you cross between the stable and unstable domain in your phase space, because K1 and K2 keep changing when they're unstable, and you obtain this limit cycle. So one way of explaining this to reach not a stable point, but a limit cycle around this unstable position that we have in the green dot initially. Okay. All right, so so that's a way of having these sustained oscillations for this system, and now we wanted to transfer that to the vertex models that we were working with. The vertex models that we have is just as standardly done. So we define an energy associated to the perimeter. So we want to minimize the perimeter, and with a given constraint on the area. Okay, the area must be preserved. Okay, but we minimize all an energy function associated to the perimeter. So altogether can be explained as minimizing, give me the positions of my nodes. So in this system, the vertex model is fully described by the center of the cells and the positions of the boundary of the cells. Okay, this membrane. So it's also interpolated through the cell centers. Okay, so the cell centers fully describe the system because the y's that we have here depends on the x. So at the end, everything depends on the x, and you minimize with respect to that energy, and you get the equilibrium positions. So there is this plus some topological changes that we'll go into that for the 3D. You minimize, and in addition we add this contractility at the wound ring, as there's an increase of myosin on this wound ring also here. So with that we reproduce this wound healing, and there is this delta parameter which says when you intercalate, so whether the cells they are allowed to be more stretched or less stretched. So you allow them to be very stretched, so it means that delta is larger than 1. You have a rosette-like configuration, and if not, you have further intercalations. So so it's how easy they are to intercalate. So this seems to be related to the fluidization of the fluid around the wound. What was interesting from all these plots, so this is the energy barrier that we have to close. So we introduce this contractility, which is an external input. And then the energy, so of course, if we allow to intercalate, it closes sooner. So the area, okay, would diminish sooner. This is different experiments, and we have in red what would be the simulation. So it begins to be 2 phases of the closure, plus the final one of the intercalations, without which you don't really manage to close. What is interesting is that besides of the intercalation rate that you introduce, all the energies go on the top of each other on that plot. When you plot with this energy versus area closure, okay, of the wound. So they all go on the top of each other, so they go faster or slower, but with the same energy profile, so following the same energy barrier, regardless of the intercalation rate that you introduce. Okay, so that was interesting, and that was vertex contributions, so cell cortex contributions versus cell bulk or the cytoskeletal contributions that you have in the cells. So it seems that it's more sensitive to the cortex contributions of the cells. And so these numbers here, this is the closure time. Okay, so it seems to be more sensitive to this, what you're having at the stiffness of the vertices. So with that, we wanted to also test our rest length method, but we went to the 2D.5, so we had also the wound closure in here, and also applying the contractility at the top of the cells, and also introducing this intercalation also between the cells. So we'll go into the topological problems that we encounter here. There are a few. I just mentioned that at the end the cells look a little bit too large, and this is somewhat related to the fact that we are not reproducing the debris, which is the dead cells that are in the wound, and they are absorbed, okay, and so they seem also to slow down the cell closure in here. So, but what about the oscillations? So we introduce this rest length base for each segment that you see here in 3D, and so what we had is also the sustained oscillation when the rest length is dependent on the size of the segment. Yeah. Okay. So I will fast. So, and that there is this different synchronization between the cells, and this is application to 2D, but I will skip here and just quickly go into the 3D vertex, which is the same, minimizing the total energy related to the cortex plus the bulk, but the bending energy doesn't seem to be very necessary, and we minimize with respect to the vertex positions. So the topological change is also described by cell centers. So you can do track who is contact with who with a dual network, which is the cell centers. So this requires to doing some flips in the mesh of tetrahedra that is behind the vertex between the cell centers, and this requires to convexify this mesh of tetrahedras. So there's other complexities, but assigning different energies to the cell boundary, cell substrate, you have different configurations that you may have. And we play with that in order to reproduce this extrusion effect that is having these cells that you have in blue here. For instance, they have less affinity, or so to say, they have a higher penalization of this cell-cell contact than the others. And so it was an exercise in order to look at the cell migration to the cancer migration, in fact, for monolayers, okay, in some cases. So we are working on that in order to have the oscillations and the sustained oscillations on that model. So this is still in progress, but at least the topological changes, that is something that was a little bit challenging. There is a viscous component that I didn't mention in order to have this stretching and compression effects that we have here, right? So. So that's why we needed these viscous effects, because it's not a pseudostatic model. So with that, I finish with the conclusions that I think I have already mentioned, but I do want to thank the collaborators in London and at UPC. Thank you very much.
Yeah, thank you. I don't know this topic at all, but I was wondering, would it be interesting to have the same parameters so that you have the same time of oscillation than what you observed in the data, and maybe understand why it goes faster or slower in some cases, or if it's always the same time of oscillation? I don't know if you see what I mean.
So the period of oscillation is proportional to the delay. So one and the other correlate each other pretty well. And in fact, if we have a delay of 3-4 minutes, we can set up the delay. The period of oscillation seems to be 3-4 minutes, and there seems to be a half period delay between the myosin signal and the deformation that is being observed. So we can put those parameters in that manner. So the origin of the parameter seems, I don't know, for my understanding, is the time that it takes the signaling to travel to the, like for the cortex, and so there are intermediate filaments, so there is some time, but with those systems seems to be orders of minutes, of 3-4 minutes, for instance, for those systems in embryogenesis. But other systems have other delays, and they have other causes that they are not cellular. It's those traveling ways between cells, so they are not that localized. So maybe questions of more tens of minutes. Maybe, so.
Thank you. Just in your wound healing models, what are the sources of the contraction in your model?
So in here, in the 2D that I presented, so we have a contractility on the top. For instance, here, there is has been measured the myosin concentration and the lateral concentration, that the two of them increase. There is no basal myosin concentration, seems to be. So, and there is an increase, and then pretty sustained, it decreases progressively, while the one on the lateral decreases much faster. So, and what we introduce is the same evolution that we've seen, so something proportional to this myosin concentration applied to this epsilon c, which is what we had around the wound ring. Okay, so it's just the ring around each. Around the wound. Around the wound. There is a contractility, so the recoil is due to the elastic state. So there is a epsilon c, and on the tissue there is an epsilon c homogeneous everywhere. So there is some contractility in the whole tissue. That's why it recoils. So there is this viscoelastic recoil, and that allows us to measure the viscoelasticity of the tissue. The amount of recoil and the rate of recoil allow us to calibrate this contractility homogeneous on the tissue. And the myosin that we have at the wound is the one that allows us to then calibrate this epsilon c that we have seen here, only at the wound ring.
One question about the diagram you showed us with the area curve, where you saw that all the curves went on top of each other. Yeah. There's just this end on the right. Why does it go back? You mean, let me see if I'm on the right. You mean this peak here on the bottom left? So this is the recoil. So the area, we have this area initial, so it expands and then it closes.
You introduced this delay time in the beginning. What is it due to? I mean, I understand that it creates oscillations, but what is it due to? How do I change it, for instance?
So how to trigger that? I pose these questions to biologists, what might be. So the cause may be from the signaling that it takes to travel inside the cell, from, okay, the triggering signal from the nuclei to the cortex, for instance, so traveling, okay, that may be the time that it takes to polymerize or have a contractility at the boundary. And yeah, there is this intermediate filament, so it seems to be between the myosin takes place and the cell contracts, there is this delay. What is exactly, I cannot tell you. So this is, for the dorsal cruciate, for instance, 3-4 minutes, in terms of minutes, yeah. Yeah.
All right, no question online. So, okay, so thank you again.
Okay. Thank you.